everyone, I'm Bharat, and today I'll be talking about a fascinating and emerging area in signal processing, which is topological data analysis. I'm excited to share how TDA can be used to unlock insights in signal processing. So let's dive in. Let's start with a quick introduction to signal processing. It involves manipulating signals like sound, images, or sensor data to improve, compress, or analyze them. Some common tasks include filtering, modulation, and compression. However, signal processing is not without its challenges. Signals are often high dimensional and non-linear, which makes it difficult to analyze them, especially when there's a lot of noise or when they need to be processed in real time. This is where TDA comes. TDA allows us to take a non-linear multi-scale approach to extract the topological structures embedded in signals. Essentially, TDA lets us transform signals into geometrical or topological objects, providing a fresh way to analyze complex data. To understand TDA, it's helpful to know a few key concepts. First, let's talk about simplexes. These are the building blocks of TDA. A zero simplex is just a point. When we connect two points, we get a one simplex or an edge. Add another point and we can form a two simplex, which is a triangle. And with 4 points, we get a three simplex or a tetrahedron. We can assemble these simplexes to create simplicial complexes, which helps us to form shapes from data points. Another fundamental concept is persistent homology, a core tool of TDA. Persistent homology tracks topological features like connected components, loops, and voids across different scales. We can visualize these features using persistence diagrams and barcodes, which show how long these features persist as we vary a parameter. It's like watching topological features appear and disappear as we zoom in and zoom out the data. Why TDA in signal processing? So why we use TDA in signal processing? Because it has several advantages over the traditional techniques. First, it's more robust against noise and outliers, making it well suited for noisy data environments. Additionally, TDA captures both local and global structures, offering a richer multi-scale representation of the data than traditional methods focused on amplitude and frequency alone. In real-world terms, this robustness and flexibility mean that TDA has helpful applications in fields such as biomedical signal processing, like EEG and ECG analysis, as well as in financial data and communication systems. Now, let's walk through the typical TDA workflow in signal processing. First, we start with data acquisition and pre-processing. We transform a signal into a point cloud using a technique called time delay embedding, which converts temporal information into a spatial representation. Next, we extract topological features by constructing simplicial complexes from this point cloud. Then we analyze these topological signatures by generating persistent diagrams or barcodes. Finally, we interpret these topological insights to make more informed decisions. One of the most promising applications of TDA is in EEG signal analysis. EEG data is known for being high-dimensional, non-linear, and complex, perfect for TDA strengths. In EEG analysis, we convert brainwave data into point clouds where we can apply TDA to extract features that are associated with different brain activity states or abnormalities. Compared to traditional EEG analysis, which often focuses on frequency components, TDA can capture global dynamics and multi-scale interactions that offer a deeper understanding of brain activity. TDA also has potential in speech and audio processing. Here we are interested in capturing unique characteristics like rhythm, tone, and speaker-specific features. TDA allows us to extract global shape-based patterns rather than focusing solely on frequency components, as traditional spectral analysis does. For instance, TDA can improve speaker identification and emotion recognition by preserving complex features even in noisy or distorted environments. Moving on to image and video processing. TDA helps us by identifying shapes, objects, and scenes in both 2D and 3D data. TDA excels at tasks like object recognition and scene understanding, which are crucial in fields such as robotics and autonomous driving. For example, it's particularly effective in dealing with occlusions when parts of an object are hidden and deformations like objects that change shapes. TDA also has applications in time series analysis. By using sliding window embeddings, we can detect periodic patterns and identify regime changes in time series data. This approach is valuable in areas like financial analysis, where TDA can help detect anomalies in stock market trends or in climate modeling, where it can identify shifts in weather patterns. TDA can also enhance machine learning models by serving as a feature extraction technique. By using topological features like Betty numbers, we can give machine learning models additional insights that help improve their interpretability and robustness. Research is also exploring ways to integrate TDA directly with neural networks, creating what's known as topological neural networks. This fusion can help us better understand how neural networks make decisions, especially in noisy data environments. While TDA is powerful, it does come with challenges. The first is computational complexity. TDA can be resource intensive, especially for large scale or real time applications. Another challenge is parameter selection, as choosing the right scales is crucial for accurate analysis. Lastly, the interpretability of TDA results is still an area of active research. It can be difficult to link persistence, homology features directly to intuitive, real world signal characteristics. As we look to the future, there are exciting opportunities for the TDA. One area is real time TDA, which involves developing algorithms that can process streaming data on the fly. There's also interest in applying TDA within edge computing in IoT, where signals could be processed directly on devices rather than on centralized servers. Finally, we may see more hybrid approaches like combining TDA with other techniques like Fourier analysis or wavelets, leading to even more powerful analytical tools. To wrap up, TDA offers a unique multi-scale nonlinear approach to signal processing that can provide new insights into complex data. Its potential applications span healthcare, robotics, communication, and finance. I encourage everyone here to consider exploring TDA further, whether for research or practical signal processing applications. Thank you. These are some of the key resources for anyone interested in diving deeper into TDA and its applications in signal processing.